Okay, so in this lecture video, we're going to discuss groundwater. So we've already talked about surface water and running water. And in that, we had talked about there being a process where precipitation will infiltrate down into the ground. And that's this water here, groundwater. So it is stored and moves about in the subsurface based on a number of factors. Primarily, those factors are pore size, or the porosity of different sediments and soils beneath the surface. So let's get into it. So groundwater makes up 94% of all fresh liquid water. Okay, so that's not the water that we talked about being stored in glaciers, which I'll get to in a future lecture. But this is the available liquid fresh water available globally. Groundwater is the largest reservoir of fresh water readily available to us as humans. We pump it out of the ground. It's already liquid. And it's stored in even places where it's fairly dry or arid. If you dig deep enough, you might find it. And groundwater stores water that feeds streams generally during dry periods. This is a really great animation. I was futzing around with it earlier and I couldn't get it to play during this recording. So I highly recommend you going to the lecture slides that are posted and clicking on this animation to give you a sense of how groundwater infiltrates and how it builds up and eventually is exposed to the surface in streams and lakes. So the key words I want you to take away here from groundwater are infiltration. So that's the water actually moving down from the surface through the sediment. The zone of aeration, that's the area where the water has moved through and is not accumulated. It's continued to sink down into what we call the zone of saturation, which is within the water table. So if this is the water table here at the very top, the part that we would drill down to and pump, the zone of saturation is below that line where it's just saturated with water. The zone of aeration is the thing we are drilling through. And you'll see here, this is an unsuccessful well because they didn't drill down far enough. And so they're still in this zone where there might be some water holding the grains together, but there's no water within the pore spaces to pump. Whereas in the zone of saturation, all of those grains, the pore spaces between them are saturated with water. Because remember, groundwater is not like an underwater lake, which is a common misconception, that there's just big hollow caves full of water. It's not like that at all. Although that does occur. When we're talking about groundwater, we're talking about the water between these pore spaces. And it is moving and flowing due to gravity. But like when we have an aquifer, you think about it like we're really just in a big sandy sponge, right? And there's either water in that sponge, and you can squeeze it and water will come out, or there's no water in the sponge and it's dry. So sometimes groundwater will appear on the surface, and here is a mountain spring. This is what they generally look like. And it's not just a big hole in the ground, it's actually just water. The water table here is above this spring at the top of this hill or mountain. This part here up at the top is primarily the zone of aeration, and then where the contours of the water table meet the side of this hill, then we start to see water appearing at the surface, and this would run down as the beginnings of a stream or river. And when it comes to the interaction of streams and rivers with groundwater, there's two main types, and that's gaining streams and losing streams. Gaining streams we call effluent, and losing streams we call influent. And note here that there's, in these two, A and B, there are intersections between the water table and the ground surface, and that's what produces the surface water that we see during dry periods when there's not actually runoff water moving through these streams. In dry periods, you can still have streams, and that's just because the water table is high enough that it's exposed at any spot where there's a stream bed. And here, the water table is high enough that it's moving water into the stream. So that's a gaining stream or effluent stream. Here, the water table is lowering. And so water from the stream is beginning to run down into the ground surface. And it's accumulating a bigger zone of aeration as this happens. And eventually, groundwater will drop if it's particularly dry, like say late in the summer season, all the rivers will be fairly low because then you have a riverbed sitting directly on top of a complete zone of aeration. And so the water is literally sinking down to the much lower water table now. And so that's the disconnected losing stream, whereas this would be a connected losing stream. So groundwater moves like surface water, but it generally takes a more windy route. So surface water exploits the contours of the land, right, and the topography of the land, whereas groundwater is mainly influenced by gravity and porosity, or sediment type. So porosity is the proportion of open space between grains of sediment, and it determines how much water can be stored in the zone of saturation here, right, and how free that water is to move around underneath the surface. So here's the water table. Here's our unsaturated zone, our zone of aeration, and the water is moving down to the water table. And here we have the saturation zone. So that's this line here. And here we've zoomed in and we see that we have open pore spaces in this sediment type here, and similarly in this sediment type over here. And so these different sediment types are going to have different zones of accumulation or saturation. And so water in a finer grained sediment type is still filling those pore spaces, but there's less water than you would have over here. So sediment type makes a big difference for porosity. And porosity varies with grain size, right? Grain sorting and grain shape, okay? So for grain size, if you have larger rounded grains, you're gonna have some porosity, but a little bit less. Rounding gives you, believe it or not, less pore space because they interlock a little bit better. If you have really poorly sorted gravel, right, or sediment, you'll have big spaces that normally would love to have lots of pore space for water to accumulate in. But if it's poorly sorted, you've got smaller grains that would go in and fill that space in. And so you have really, really small amounts of pore space in a poorly sorted gravel. And then in an area where the grain sizes are irregular and the grain shapes are irregular, sort of angular, you can get much larger pore space. And so this is ideal right here, especially when we're looking for aquifers and places to pump for groundwater. So porosity is how much water it can hold, and then permeability is how much water it lets through, right? So these two things are very much related, but when you measure the connectivity of pore space, that gives you a sense of how much water can move through the ground surface or underneath the ground surface. If you have no pore space, right, so it's non-porous and has low porosity, you have low permeability. If you have unconnected pore spaces, you're porous here, right? You do have pores with water being filled in, but you're non-permeable here because the water can't move from one pore space to the other and make its way through the ground subsurface. Then if you have connected pore spaces where the grains, there's enough water in there where the grains have begun to separate away from each other because the water pressure is pushing them apart, then you're porous, just like you are over here, but now you're also permeable. And that means that water can move through this area based on the connectivity of the pore spaces. And permeability varies with, again, sediment type. So if you have gravel, you have large sediment class. And so you have high permeability and high porosity. And when we grade basically how much water you pull out of something based on how permeable it is, we call that the specific yield. How much water can that sediment type yield if we were measuring how much is moving through it, or if we were measuring how much we can pump out of it. Fine sands, also, they have moderate drainage, right? So if you were on the surface, this would be something that would drain. Similarly, if you had mostly gravel at the surface, any rainwater would drain right through it, no problem. Same with fine sand, only a little less so than gravel, but still pretty good. It will drain and it will run down through the zone of aeration into the zone of saturation, or the water table. And that water can move through both of these really well over here and okay over here. And then you have slow to no drainage. So if you have a clay sediment at the surface, you're going to get not a lot of infiltration, not a lot of permeability. And so that has a pretty low specific yield because the grain signs are so small, there's barely any porosity there, and so low permeability. And then solid rock is impermeable. So there's no porosity at all in solid rock because it's solid rock, it's not sediment, right? So there's no space at all between any of the mineral grains in this case, or any of the sand grains if you have a sandstone, because all of that pore space is filled with some kind of cementing sediment, like a clay or something like that. So if this was the surface upon which you were to build anything, when it rains, this is all just going to be runoff. Nothing infiltrates at all. So this process of infiltration and differences in porosity are what forms aquifers. So an aquifer is a water-saturated geologic formation with porosity and permeability sufficient to yield water, right? And water in significant amounts. So that's the place where the water is stored. And this is usually capped below or above, or both, by what we call an aquitard. So to retard something is to slow it down or stop it. Okay, and so this is aquitard, means stopping water, basically, or water stop. And that's a geologic formation that lacks permeability or porosity, and it restricts the flow of water. And in this photo down here, or photo, it's not a photo, in this cartoon down here, we see an aquitard that we call a perched aquitard. And that's where you would have had during sedimentation, when things were being deposited, you would have had a bunch of sand being deposited and then a bunch of mudstone being deposited. And what this does is during some kind of transgression or regression of sea level, these different sediment types were being deposited. And so you might have just had a brief time when there was mud being deposited, and then sea level rose again. So here we had sea level drop from this sandstone up to this mudstone, or sea level rise, I mean, as we had a sandstone being deposited in one spot and then a mudstone being deposited in one spot. But then sea level switched it up and started to fall, and then we had sandstone being deposited again. And if that sandstone is permeable, you can get infiltration down. It's going to hit this mudstone layer, and it's going to have a water table here that's kind of perched up above the main water table. And if you were to drill down into this, you could have a successful well there, okay? So if you were building up on the top of a mountain and you wanted to put your well there for your house, you would do a bunch of drill sites to decide where you wanted to drill your well based on whether or not you had a perched mudstone aquitard here. Then if you go down valley, you would see that you have the main water table interacting with whatever stream is down in the bottom of that valley there. So water coming into an aquifer is something we call recharge. And the amount of water being removed from an aquifer, either through natural process, but most likely through pumping, through human interaction, we call that discharge. And let's talk a little bit about static water tables and unconfined aquifers. So an unconfined aquifer is an aquifer that's exposed to atmospheric pressure changes and is directly linked to the surface through its pore space. So down here below in some area that's not pictured in this drawing here or this graphic, there would be some kind of an aquitard down below that allows this water table to be here in the first place. But you'll notice there's no aquitard over the top of it, okay? And when you have that, you have water directly coming from the surface through precipitation, moving across the ground surface or falling directly onto the ground surface, and it runs down through infiltration into the water table. And it's also subject to pressure because there's atmospheric pressure being exerted on the land that sinks down into the pore space in your zone of aeration here. So there's atmospheric pressure there as well. But there's also the effects of negative pressure or vacuum. So let's say somebody drills a well here, right, for their home and their farm. Somebody drills a well here really deep. This is to maybe water fields or something like that, and the same here. And you have different depths of the drill borings here. And so if somebody has a well here and they're drilling, and then somebody has a well over here and they're drilling, and then some company or some other entity comes along and drills a much deeper well, what that will do is it will begin to create negative pressure in this water table, and it will begin to suck water down to this lowest point, as we see here. And what we call this is a cone of depression, kind of much like being in school during the summer. Maybe you're also in a cone of depression. But anyway, this will pull the water down, and what it could do is lower the water table at these outer edges here and drop the water table below the area where these wells were once pumping. And so these smaller wells now go dry. So a very important thing to take away from an unconfined aquifer or a static water table. And for unconfined aquifers, the amount of drawdown, so that's the difference between static water table and the level after it's being pumped, is related to permeability. So if you have a really steep cone of depression, where it's moving over here and then it suddenly drops very steeply near the deeper well, that's due to low permeability in the sediment. If there was high permeability, you would have a much more gradual cone of depression moving across here because that water is able to move through all of this sediment no problem, right? But if this was all lower permeability, like a muddy sand or even a mudstone, this well here wouldn't be pulling water from over here. It would just be pulling water from right around the well. And so you get a steeper cone of depression. You can also get overlapping cones of depression based on the seasons. And so overlapping cones of depression, you can imagine a cone of depression being created by one well, and then that is being overlapped by a cone of depression being created by a much larger well. And so let's move on to pressurized water or confined aquifers. So a confined aquifer is enclosed by two impermeable layers or two aquitards. Here we have an aquitard that's perched, and it has an unconfined aquifer on top of it that's subject to precipitation, like I mentioned just a few moments ago. But below that, you could have another sandstone layer. Remember our transgressive series, we get mudstones and sandstones and limestones being deposited in different sequences based on sea level rise and sea level fall. And so you can have a mudstone layer with a sandstone layer above it, followed by another mudstone layer above that. And here we have no interaction with atmospheric pressure or with any kind of water infiltration from the zone of aeration. And so this water here in the confined aquifer is cut off from the surface in many, many ways. And let's talk about what that means. So if you have an aquitard on the top and the bottom and you have a confined aquifer, Remember, these layers, generally sedimentary layers, have been deformed by tectonic processes. So you'll get folding like this. The folds will be exposed to the surface as mountain ranges. And those mountain ranges, because of the way the fold eroded here, which I'll talk about when we get to relative age dating, what you have here is you have an angular unconformity. This is where a fold would have been going up across this way here, but it's since been eroded flat this way with layers kind of sticking up. And so here you'd have sandstone, right? And then here you'd have a mudstone kind of mountaintop, and here you'd have another mudstone mountaintop. And so when it rains up in these mountainous areas, it sinks into this sandstone layer and it flows down like a water slide through this confined aquifer. So what does that mean? Well, let's say you have a little farmstead over here and you've drilled down past the zone of aeration through your top aquitard into your confined aquifer. If you know anything about hydraulic pressure, you'll know that the water that's up here and the atmosphere that's up here is pushing down on this, because this part is exposed to the atmosphere. That pressure means that you have a higher pressure gradient down here. You have the same pressure surface up here at the top that you have down here. This is the basics of sort of all hydraulics, if there's any engineering students in the class. When you're pumping, let's say, the jack on your car, you're pushing a cylinder of fluid into another cylinder of fluid, and you're getting an equal pressure gradient between the two. And so here, when you drill into this well, the water is under pressure. So if it's tapped, the water will rush up, trying to reach this equilibrium up here of the surface pressure, which down in this valley is above the, it's above the ground. It's at some point relative to the elevation of the water up here. And so that water is going to flow. And what we call that is an artesian well. And here's just to kind of further illustrate what I was just talking about. Here you have a well number 1 up here on the slope. And it's not under enough pressure because you see the pressure gradient is still underground here. So when you pump this, it's not going to be flowing. It's still artesian because it's still confined. So it's still kind of pristine water that's been confined. It's not subject to pollution and contaminants and things that might run down through the infiltration process. But it's not under pressure. So it's clean water, but you got to pump it. Down here, you're getting clean water, but you don't have to pump it. It's coming out naturally on its own based on the pressure gradient. So we'll see that here zoomed in. Here's our recharge area. Here's our discharge area. This you would pump. This would flow and you would not. So that pressure surface, I'll explain a little further. So if the pressure surface or the potentiometric surface is greater than the ground surface, so above the ground surface, like in those pictures we just saw, you get a flowing well. And when it's lower, you have a non-flowing artesian well. So what's the advantage of an artesian well? Well, you don't have to expend as much energy to pump it, and it's better protected from contamination. Because again, that upper aquitard layer is preventing any contaminants from leaching down through the soils and the sediment and it doesn't reach the confined aquifer. So let's talk about groundwater storage and management. So to properly manage our water resources, it's really important to know the amount of water stored in an aquifer and the sustained yield or the expected yield over a long period of time. And this has everything to do with the recharge rate, so how much water is being replenished to the aquifer through the recharge zone, like through the movement of groundwater or through precipitation primarily, and the discharge rate, so how fast are we pumping it out. And as a geologist or a hydrologist, one would go out into the field and you'd have a well, and then right next to it you have a monitoring well. And what we would do here is, and I've done this before, some of you, if you take a hydrology class later on, you'll do the same thing. You'll basically stick a pump down your well and you'll start pumping water out at some rate, gallons per minute or liters per second, or whatever rate you're pumping it out at. And then you'll stick a sensor down in the monitoring well that has a little hydrostatic sensor, and it measures where the water level is at any given time. And so you can pump for a while and let it drop down below, and then you turn off your pump and you let it rise back up to the meter, and you time that. And so you can figure out, here's how much water we're pulling out over some amount of time, and here's how fast it's filling back up over some amount of time. And if it's filling up faster than the discharge rate, then you have then you can basically calibrate your discharge rate to get the most water out while it's still recharging. And so these are viable, sustainable pumps, and that's what sustainable yield is. So let's talk about some problems with groundwater. They are overpumping, primarily. And with overpumping, we see groundwater mining, we see subsidence, we see sinkholes, and we see saltwater incursion. And then also a main problem with groundwater is contamination. So let's dig into each of these. So for groundwater mining, that's when we have the sustained yield is the amount of water that can be withdrawn on a long-term basis without depleting the resource. That is, discharge is equal to or less than recharge. If the amount of withdrawal exceeds the sustained yield, it creates this overdraft condition called groundwater mining. And that's when we start to pull water out of the ground faster than it recharges, as I've said. And so we're really mining it, and we have an unsustainable yield. And so now water in this particular aquifer has become non-renewable if we continue to pump at those current rates. And the effects of this are, as water is being pumped from the water table, you can get water pulling up that can dry up certain wells, like we talked about with cone of depression. But also there's some, at lower topographies, so sort of downland, you can start to see streams that were maybe once gaining streams or effluent streams become influent or losing streams, and eventually they can become disconnected losing streams, and so that stream completely dries up. So that's one effect. We can also imagine if we began to pump water so much that it drew this whole water table down to this level here at this deepest well, these other two wells are no longer producing any yield. So the problem with groundwater mining, again, causes wells to go dry, increased costs, so more energy is required to pump water from the dropping levels, and it can cause ground subsidence. Also, and I'll talk about subsidence in a later slide, but also we have groundwater problems around saltwater. So what can happen here is if you have fresh groundwater at a coastal area, you have, because of density differences, you'll have salty groundwater that's intruding down into the sediment from the ocean, and that moves down this way, but because of density, it will move down this way underneath the fresh groundwater, and you get this kind of, not invisible barrier, but you get this non-solid barrier of just fresh groundwater sitting atop salt groundwater. And this happens all over near coastal areas, and in some places even just in the ocean. There's this famous spot in Mexico where you can scuba dive down. I've never been, but you can scuba dive down through fresh water, and then you can swim right past into the salt water. If I were to stick a pump down into this through the zone of aeration into the groundwater, and I start to pump, but I overpump, I'm going to create something like a cone of depression in the salty groundwater. This is sort of an upside down cone of depression here. And what you'll start to do is you'll be no longer pumping fresh groundwater, and you start to pump salty groundwater. And so this pump is now producing salt water. No good. You can also get sinkholes. So this is when basically slightly acidic groundwater moves through mostly limestone. As we know, limestone reacts with acid if you have a slightly acidic water based on a number of different factors, how much dissolved carbon and carbon dioxide you have in there. That carbonate is going to, or that acid is going to react with these carbonates here, and it's going to begin to hollow them out. And that's how we get caves, right? Like limestone caves, like down in Indiana, Kentucky, like Mammoth Cave, places like that, like in Missouri and elsewhere. When you get that, you'll have areas where groundwater is moving through here, and in these small caves, you will have areas that are filled with water that's moving through and dissolving the cave as we go. So imagine this is filled with water. And what will happen is if you begin to pump and the groundwater drops enough, this cave will get hollowed out. And when that happens, if there's enough overburden up here or enough weight, the surface ground will start to sink down into these caves. And you get something that looks like this, where the ground will collapse down into an area that was once being held up by the water pressure of the water, filling this like a water balloon. And when you remove that water, now you have an empty balloon and it falls down. We also get ground subsidence. And this is where excessive groundwater gets pumped out to the point where the pore spaces that were once filled with water and sort of holding the ground up, the pore space is now filled with air. The sediment will start to slowly compact, and the actual ground will begin to just sink. And here's a picture of, they've put this post up here and they've shown you, this was in 1977. Here's where the ground is in 1977. And it's not like they had this pole here the whole time. What they're trying to show here is that this is where the ground was in 1925. So relative to the elevation of the ground here, in 1977, the ground was once up here. So we lost about, let's see, that guy's probably 6 foot, 12, 18, 24, 30. So we've had about 30 to 35 feet of subsidence just over a 52-year period. And this is because they overpumped here in this area here, maybe somewhere in the Midwest. Another issue with overpumping of groundwater is contamination. And this is contamination within a well. So we often have storage tanks in this zone of aeration here. We might have a pipeline in that zone, and we can get contaminants that run down into groundwater this way. But if the general flow of groundwater is in the leftward direction here, any of those contaminants that get into the groundwater flow away from this well that this house is using here. That's all fine and good. But let's say then they want to irrigate this field over here to the right. So somebody comes along and drills a well here, and it's deeper than the well here. That creates a cone of depression overlapping with this cone of depression. And so that even though the groundwater is flowing this way for the most part, up here at these areas where the cone of depression is, that groundwater is flowing towards this well now. And so this house is pumping septic water or any kind of contaminant that would have been moving down gradient here is now being pulled up into the well. And so now this small well is contaminated by sewage bacteria. Another thing that's very important is to know the subsurface geology whenever you're drilling. So up here in figure A from your textbook, we have a septic tank up here on the left in figure A, and in figure B we have a septic tank here. And one thing that's important to note is that sediment will oftentimes filter out any contaminants based on the distance. So down here in figure B, we've got, let's say we have 100 meters here, right, between these two houses. And here we have a well. And the septic tank is contaminating water down into this zone of aeration. But by the time it reaches down into the water table and makes its way over here to this well, the sediment has filtered out a lot of the contaminants, and so this well is producing clean water. If we take that same distance, but we have a cavernous limestone here, even though we're still 100 meters away, it's hitting this non-permeable layer, and that water is not moving through the zone of aeration, a sandstone like down here, hardly at all. It's just running right onto this limestone or mudstone, and it's moving right down this mudstone down here to the well. So it's being delivered much too quickly to be filtered out by the sediment, and so this is delivering contaminated groundwater to this well. So let's talk, we'll finish up here with talking about some solutions to groundwater problems. So as you can imagine, for groundwater mining, we just need conservation. So we need to conserve the amount of water that we're pumping out of aquifers, and we need to make sure that we are maintaining a sustained yield. That is, our discharge rate is lower than our recharge rate. We can also do some artificial recharge, so we can move water from other places that have higher recharge rates than discharge rates. In an aquifer, we can pump that water to a place where the discharge rate is higher, and we can artificially recharge that through artificial means. We can minimize sources of pollution, so we can just make it so that we're not polluting the air and the groundwater nearly as much. And so less contaminants will get in the groundwater. And we can identify and protect watersheds and recharge areas so that no contamination is entering the water table at those areas. And I want you to think about some more areas where this might be the case and talk about that in the discussion prompt for this week. So that concludes groundwater. Thank you very much. We're going to move on to glaciers next. So have a great day, and I'll see you guys in lab.